Hey everybody, welcome back to another video. So in this video, we're going to talk about an introduction to the vascular system, and we'll talk about the basics of blood pressure, okay? But before I get started and talk about the vascular system a little bit, I want to just take a few seconds and mention the functions of the vascular system. And you guys should already kind of know this. The functions are to just deliver O2, remove CO2, nutrient delivery, removal of waste like lactate, distribution of things like hormones, transporting red blood cells, immune cells, and a little bit of temperature control as well. Okay? Now, another important fact when we talk about the vascular system is that every single organ or tissue in your body is getting a vascular supply. But the question is, are they getting the same amount of blood from the vascular system? And the answer is no, okay? So we have a set amount of cardiac output at rest, which is about 5 liters. You guys should know that. And because there is a set amount, each organ receives a specific different amount, okay? So there is something called a selective distribution, meaning that not all of the tissues receive an equal blood volume. And what determines where and how much each tissue is getting? Well, there are intrinsic mechanisms, and there are mechanisms that are regulated by the nervous system, which again, we won't talk about in this video, we'll talk about in the future videos, okay? All right, so now with all of that out of the way, let's go ahead and dig into the components of the vasculature and then the types of the vessels. Now guys, if you liked the video, if you enjoyed, if you learned something, please consider subscribing, consider liking, and let's get into it. So when we talk about the vasculature, okay, we can actually split the vessels that exist within it into two types. We can say that there are macro vessels and there are micro vessels. Okay, so micro and macro vasculature. What does the macrovasculature contain? The macrovasculature contains things like your veins and your artery. Okay? What about your micro? Well, your micro contains other things. It contains these smaller veins called venules and a smaller version of the artery called arteriole. Okay? It also contains these very, very specialized tiny vessels called capillaries, which are actually really, really good for exchanging gases and nutrients, okay, and other things. Now, just to get you guys introduced, I'm going to go through this little schematic that I've drawn here to show you how the macro and microcirculature work together, okay? So let's start out from the heart, okay? From the heart, we're going to push blood out into this artery, okay, this big giant artery, which you can imagine is the aorta, okay? And the blood will continue to go through this actual artery, okay, until this artery splits. What does it split into? Well, it splits into even smaller arteries. Not arterioles yet, they're just smaller arteries. And as soon as we reach this tissue, and this tissue in this case is the kidney, okay, as soon as we enter the tissue, the vessels that are now inside of the tissue are no longer called the arteries. They are now called the arterioles. These little red vessels here, these are all now arterioles. So here we have some, proximal arterioles that will keep dividing and dividing into these terminal arterioles. You see these little tinier terminal arterioles. And as they divide into these terminal arterioles, they will finally stop being arterioles and divide into something called a capillary. And these capillaries are, drawn in purple here, and they're very, very special and specialized for nutrient exchange, gas exchange, and etc. After the nutrient gas exchange and etc. has occurred at the level of the tissue, what we end up doing is that this capillary is going to split into these little smaller veins that we said are called venules, okay? And these venules are going to carry the blood out of the tissue, okay? You see that? They're carrying the blood outside of the tissue. And as soon as we leave the tissue, they are no longer called venules, they're called veins, okay? And you see that the vein is responsible for taking the blood back to the actual heart. So just to take home points from here, the macro circulation is going to take blood from the heart and back to the heart. Okay, so from the heart to the organ and from the organ back to the heart. The microcirculation, everything, all of it resides inside of the organ, inside of the tissue itself, and they are responsible for spreading out the blood flow within that tissue. The arterioles specifically, as we will see in a second, are responsible for regulating the amount of blood that this tissue is going to get. The capillaries are responsible for gas exchange and nutrient exchange, and the venules are responsible for pushing the blood back into the veins and delivering back to the heart. Okay? So now that we actually know this, and what are the components of the vessels, what's the schematic look like, let's go ahead and look at the types of vessels that we can find within the vasculature. So starting out, I have this diagram here where we have a vein, a large elastic artery such as the aorta, a capillary, and an arteriole. Okay? Now, I know I could have included other things such as the venule or a muscular artery, but that would be too complex for this video. So we're going to keep it simple, and we're just going to talk about a large elastic artery such as the aorta, a capillary, an arteriole, and a vein. Okay? We're going to talk about the different layers they have, what is the difference between them, what are their functions, and all of that. Okay? And where can you find them? In the vascular tree, right? Because this is what we call the vascular tree. Now, a large elastic artery, right? We said a good example of that would be this aorta right here. So here we can say the aorta is a good example of a large elastic artery. What's a good example of a vein? Okay, well, this specific vein, a good example of it would be, for example, the inferior or superior vena cava. In this case, the superior vena cava. What about a arteriole? Well, the arteriole, remember, is the one that is actually entering the tissue. So we can say that this guy right over here is the arteriole. Okay, and actually all of these are arterioles. And depending on which level they could be distal or proximal arterioles, doesn't matter. Okay, just know that this is an arteriole because it's entered inside of the tissue. It's supplying the blood into the tissue now. What about a capillary? Well, here's a capillary right here. That's a capillary. And of course, if you want an example of a venule, then you would start talking about these. Okay, but now you know where we can kind of find an example of each of these. Okay, well, what are the actual properties of them, and what are they made out of? Because all a vessel is just a whole bunch of cells and a connective tissue. Well, good question. Let's go through this. So here is the large elastic artery. Okay, let's go through the layers, working our way from the inside to the outside. Okay, at the most inside layer, we're gonna have this cell here. This cell that is facing the blood, okay, the blood will actually be flowing through over here, okay, and this is a kind of cross section of the actual artery. So how the artery looks like this. If I were to cut it right here in the middle and then look at it from a bird's eye view, that's what I would see. Okay, so from the inside layer, you have this dude right here. Okay, this dude right over here, and that guy is called the endothelium, or the endothelial cell. Okay, endothelial cell. Okay, and this cell is the cell that is actually lining the inside of this artery and is the one that is interacting or facing with the blood. Okay, working our way a little outward, I see this little purple a bit, and this purple bit is just going to be a basement membrane. The basement membrane, all it is essentially just the extracellular matrix that is right behind the endothelial cell. Okay, and the basement membrane, if you want to know, is made up of like type 4 collagen and laminins and all that stuff. Okay, but this is the basement membrane. All right, working our way one more layer outwards, I see this thick, giant muscular layer, okay, of smooth muscle, okay? And you'll notice that, again, the aorta, as thick as it is, and it's got a very, very, very thick, smooth muscle layer, okay? And we can compare that later to all the other ones. And then another one that we're going to actually see here, this layer in purple, is the elastic layer, okay, or the elastic lamina, if you will. Sometimes this is called the external elastic layer. Okay, so external elastic layer. And then the final layer is going to be this connective tissue layer, which I'll just abbreviate as CT. And this connective tissue layer is really just made up of a whole bunch of collagen. Okay, again, if you're interested, it's made up of type 1 collagen actually. Now, all of these layers, Ooh, actually, you might be thinking, well, you said we have an external elastic layer. What about the internal? The internal elastic layer are all of these little, you see these little spindly things? These are all the internal elastic layer, and they're studded in between the actual smooth muscle cells, okay? So if I kind of just, pick on one of these guys here, I can say that this guy right here is an elastin fiber, okay? And let's do a little smaller. So this guy is an elastin fiber, okay? But what does an elastin fiber look like, and what does it do? What does it do and what does it look like? Well, I'll tell you what it does, or one of its characteristics. The elastin fiber is extremely distensible, meaning I can stretch it a lot, and it also has a very high recoil property, okay? So after I stretch it, it'll immediately recoil back, all right? And this, if you guys remember from the cardiovascular video, I'd mentioned that the aorta exhibits something called the Wynn-Kessel effect. When we push blood into it in systole, its walls are going to expand, and then at the diastolic phase of the heart, it will recoil back, push the blood out, and it will turn the intermittent flow that the heart was giving to it into a very continuous flow, so that at any point in time, we have blood circulating within our system. That was the role of the aorta because of its Wynn-Kessel effect. But really, if you want to look at it at a cellular level, the thing that is allowing for the Wynn-Kessel effect to even occur is these elastin fibers. The presence of these elastin fibers makes the aorta very distensible and have a high recoil. Okay, distensible, you can think of it as compliant. Okay, it has a very high compliance. So what does this elastin fiber actually look like? So let's take this elastin fiber and let's zoom in on it. Here's what I would see. Here's what I would see right here. Okay, so how do I know which is which? Well, this right here is the elastin fiber when it is relaxed. So when it's not being stretched, okay, it looks like this, all coiled up, okay? And what happens when it is stretched? Right here. This is the stretched version of it. Notice how when it stretches, all of these coils open up and it's able to accommodate a greater space, all right? So when the aorta during systole is getting all that blood pushed into it, what's going to happen is that blood will stretch out the walls of this actual aorta, stretching out the elastin fibers, allowing this aorta to distend. And then after, when the blood is gone, okay, this guy will go back to its original shape in the relaxed form. Well, why does it do that? Because remember, elastin, one of its properties is that it's got a high recoil. So after you stretch it, it immediately wants to recoil back, all right? And that's what's going to happen. Now, technically, if you really want to be clear, this entire thing is an elastin fiber, and so is this. This is an elastin fiber, but one of these little blue things is an elastin molecule, okay? All right, so that's a little bit about the actual aorta. What else about the aorta? What else can we say about the aorta? Well, I have something written here. I have written that the aorta is a conduit vessel. What does that mean? What does it mean to be a conduit vessel? Well, a conduit vessel is going to bring blood from the heart to the organs without actually impeding or changing blood flow. But how is it able to do this? How is the aorta or any of these arteries able to do this? Well, first of all, they actually have a low resistance to blood flow. Okay, so they have a low resistance to blood flow, and I'll abbreviate blood flow as BF. But how come they have a low resistance to blood flow? Well, think about this. Look at the diameter of this artery. It's pretty darn huge. Now, you guys tell me something. If the diameter of this artery was smaller, would there be more resistance to blood flow? Would it be easier or harder to get the blood through a smaller diameter? Well, the answer is it would be harder, okay? So these guys have a low resistance to blood flow because they have a high diameter, okay? Another thing is that they have an extremely high compliance due to that elastin that we mentioned, okay? And another thing is that they actually have very low contractility. And you might be thinking, well, hold on a minute. They have all of the smooth muscle layer. How come they have a very low contractility? Well, although they do have smooth muscle, you will rarely see the aorta contract, and it is not very well innervated, the aorta, the elastic artery specifically, okay? And in fact, this layers of smooth muscle are really more here as a cellular bulk in order to allow the elastins to kind of latch onto something. But anyways, another reason that allows this aorta to be a conduit vessel, on top of being having low resistance to flow, is that it's very strong, okay? Meaning it's able to withstand the pressure that the heart pushes into it. And this very strongness is because of the fact that it has high amounts of collagen, okay? High amounts of collagen, all right? So again, one more time, the aorta is a conduit vessel which brings the blood from the heart to the organs without impeding the blood flow, okay? Or changing blood flow. And how does it do this? Well, it's got a low resistance to blood flow, right? And, if you guys remember your Poiseuille's law, flow equals to pressure over resistance. We know that if my resistance to blood flow increases, my flow will go down. But we don't want that. We want the aorta, which is a conduit vessel, to bring blood, okay, from the heart to the organs without changing the flow, okay? So what needs to happen is it needs to have a low resistance so that the flow remains high, okay? And the reason why this resistance is down is because it's got a high diameter, a high compliance, and a low contractility, okay? Because think about it, if it had a high contractility, these smooth muscle cells would actually squeeze on the diameter and make the diameter smaller, okay? Anyways, that's all of that. So that's why the aorta is a conduit vessel. And the main takeaway point from these guys is that they have thick, elastic walls that are built to withstand high pressures. What kind of pressure that's high? Well, the pressure that's coming from the left ventricle, okay? Now, let's go ahead and talk about the other one, which is let's talk about the veins first. So the veins, just like the arteries, they're still part of the macrocirculation, but what you'll notice immediately is that they have a thinner wall. You'll notice that they have a way thinner wall compared to this thick wall over here, okay? And while the arteries were able to withstand very high pressures, and they were a high pressure system because of the fact that they had this elastin, okay? Remember that elastin made them very compliant, made them handle all these large pressures. These guys, they don't have elastin, okay? Maybe they have a little bit. Sometimes some textbooks say they have a little bit, but I didn't draw them here, so they don't have much of elastin. And because they don't have much of elastin, they can't really distend, and that makes them very much optimal for being a low pressure system, okay? And they're a low pressure system. And we'll see a little bit later how that low pressure also comes about. Another thing is because they're a low pressure system, they are kind of going to act as a capacitance vessel or a blood reservoir. What do I mean by that? Well, a capacitance or a blood reservoir means they're kind of just holding on for the blood. They're holding on to the blood. Okay, why are they holding on to the blood? Again, I want you to remember Poiseuille's law. Poiseuille's law says that the higher the pressure, the higher the flow. Well, if the pressure inside of these veins is going to be low because they're a low pressure system, doesn't that mean the flow inside of them will be low as well? Exactly. Now, if the flow inside of them is low, and remember, flow is just the speed at which the blood is moving throughout the vessel. If the blood is moving at a lower speed inside of these veins, that means that it's actually staying inside of the veins for a longer period of time and moving a bit slower throughout them. That makes these guys a blood reservoir, okay? And in fact, at any given point in time, because the blood is moving so slow, your veins are going to be holding about 60 to 70% of your entire blood volume. So 60 to 70% of your blood volume is going to be within your veins. Okay, so now let's take a look at the layers again. Again, you will notice a connective tissue layer, a smooth muscle layer, okay, so smooth muscle cell layer, This little purple layer, which is again our basement membrane, which I just told you is basically just the extracellular matrix for the endothelial cells. Okay, so the endothelial cells right here. Endothelial cells, which again are the side that's facing the blood. Now, something interesting about the veins is that because they are a low pressure system and the blood doesn't move through them as fast because of the low pressure, they need a way to move blood forward, okay? And they need a way to move blood forward against gravity. Because if you remember, the arteries are kind of moving with gravity, whereas the veins, they have to bring blood back to the heart. They're moving against gravity. So how do they do this? Well, they developed a special kind of structure or characteristic. If you look at a vein sideways, you would notice this little valve. And all this valve is the endothelial cells, these little blue endothelial cells right here. They're actually turning themselves inwards, okay, and creating these little valves. Now, how do these valves actually function? Well, here's the blood that would come in, okay, and this blood needs to open up these valves. Well, how? These guys are one-way valves, just like the ones that in the heart. They're pressure operated. If the pressure on this side of the wall increases, these valves will open and allow the blood to actually come out. Okay? So how does that happen? One of the most common ways is that majority of these veins are surrounded by muscles. Okay? And when these muscles contract, you know what's going to happen? They're going to push on the walls of this vessel. They're going to increase the pressure here. Okay? Imagine these muscles actually squeezing the heck out of this vein. And when they squeeze it, they increase the pressure. And you can see that the blood is now going to move up. Okay? So pressure in here increases. We open up the one-way valves. Blood moves up. Some of it will pull back down here. Close these valves again until the muscle moves again. Okay? That's one of the ways in which blood is actually moving through the veins. There are other ways, but we'll talk about them in a different video. And actually, one of the ways is through the sympathetic nervous system innervation. That's right, this smooth muscle layer, while it is thinner than the ones that we have in the artery, and actually the ones that we have in the arterioles as well, it is still there, and it does receive a small amount of sympathetic innervation, and the sympathetic nervous system can actually stimulate these muscle cells, these smooth muscle cells, to contract, and when they contract, they actually again increase the pressure here, open up the valves, and push blood. Okay, so that's another thing that these guys can do. All right, so now you guys know the function of the large elastic artery and the veins. Okay, with that said, now let's go ahead and talk about the arteriole. Okay, the arteriole is very interesting. It's kind of like a smaller artery, okay, with some structural differences. Okay, again, if you want to look at it from outside to inside, we have the connective tissue layer, which again is just made up of a whole bunch of collagen type 1. And then you have the smooth muscle layer, okay, which is, again, not as thick as the aorta, but you will be surprised to know that it is much more contractile, okay? And again, smooth muscle, and it's very contractile, actually, very contractile, the most contractile. And then again, you see this basement membrane, like I said, extracellular matrix made up of collagen and laminins, collagen type 4 specifically. And then this guy right here, the endothelial cell, again, the side that is facing the blood. Now, why do I keep saying that this smooth muscle of this guy is actually going to be very, very responsive, very, very contractile? Well, because not only is it available in a good amount, but also if you take a look over here, it receives plenty of sympathetic nervous system innervation, okay? So, whereas you can see before over here, there was like this many, now we got a lot of smooth sympathetic nervous system innervation. So it's highly innervated smooth muscle cell and highly contractile, okay? They exhibit a tone, if you will, whereas the veins, they don't exhibit any tone, okay? We'll have another video discussing in detail how smooth muscle cells contract. But because of this, okay, the arterioles count as one of the highest resistance vessels, okay? So they count as one of the highest resistance vessels because of the fact that they're extremely contractile. Now, you will remember that I said that the artery is actually very low resistance to blood flow, and that's because it's not very contractile. These guys, okay, not only do they have a smaller diameter compared to the artery, but they're also extremely contractile. Another thing is they're not very compliant, as in they don't have any elastin. Okay, so all of those things are going to make them a very, very, very high resistance vessel. Okay, and in fact, we'll look at a chart in a second, but you'll see that the largest pressure drop from the level of the arteries occurs at the level of the arterioles. If you don't understand what I'm saying now, trust me, you will in about 5 minutes. But okay, that's about the arterioles. They basically got muscular walls that control blood flow, and they're the highest resistance vessels. And again, they control blood flow to the capillary level, right? Because if this right here is the arteriole, right, and downstream of it are the capillaries, you can actually think of it like this. Here's an arteriole, here's the capillaries. If this guy contracts and lowers its diameter, the capillaries are not going to get any blood flow, okay? Therefore, they're going to rob that tissue of blood. So the arterioles, that's why they're the highest resistant vessel. They control blood flow inside of the tissue, which, by the way, can affect your mean arterial pressure or your blood pressure upstream, okay? That's actually another concept I wanted to talk about. Let's come back to the vascular tree. When I mention upstream and downstream, you have to know what I'm talking about when I'm talking about the vascular tree. So when I say upstream of the capillaries, what am I talking about? Upstream of the capillaries would be the arterioles. Upstream of the arterioles would be the arteries, okay? When I'm talking about downstream of the capillaries, I'm talking about the venules, okay? And furthermore, downstream of the venules, it'll be the veins, okay? So when I say that blood is actually moving through the actual vasculature here, okay, going into these little arterioles. But when these arterioles, they contract and they vasoconstrict, that means that their diameter gets extremely small, so that blood can't move through them anymore. What they end up doing is they're going to back up the blood, okay? The blood is going to actually back up now this way, okay? Why? Because this area is now constricted. If this area is constricted, this capillary is not going to get blood flow, and the blood that was initially going to go here is going to back up, and it's going to increase the blood pressure upstream of the arterioles, okay? Whereas downstream, the blood pressure is fine, but upstream, it's not, okay? So that's just a concept that I wanted to get across to you. Now, back to the arterioles and the capillary. The capillaries, they're going to be the easiest one of them all, okay? Part of the microvasculature. They have very, very thin walls, as you can see, okay? Compare this to the walls of every other one of these vessels. Extremely thin walled, and that's great because remember, I told you the capillaries are designed for exchange, okay? They are for exchange. Exchanging what? Exchanging nutrients, gases, okay? And other things. Now, another thing you got to know, again, they have a basement membrane again, and they have an endothelial cell layer, okay? And that's the only two layers they have. That's it, okay? Which is great because they need to be as thin as possible, so things like O2 can easily diffuse in, and things like CO2 can easily diffuse out, okay? And maybe other nutrients as well, all right? Okay, so that's going to finish it here on the first page, including the component of the vasculature and the type of the vessels. Now let's go to the next page real quick, and let's talk about, okay, what determines blood flow, okay? So now we know what kind of vessels we have, okay? And I talked a little bit about flow and pressure, but now let's get a solid understanding. What actually determines blood flow inside of the vessel, okay? So again, first of all, I need you to recall that Poiseuille's law right there, that blood flow, okay, equals to a change in pressure over resistance. What does a change in pressure mean? The change in pressure refers to the pressure that I enter the vessel in and the pressure that I leave the vessel with. So the P1 subtracted by P2 is my change in pressure. And that is the formula for it, right over here, okay? So a change in pressure equals the pressure that I enter the vessel in and the pressure that I leave the vessel in, okay? Now, I know this is one continuous vessel, but maybe it'll be easier for you to understand it this way. You can imagine that this part of the vessel I'm going to enter in with a from an arteriole, okay? And then this side, I'm going to leave from the venule, okay? And that somewhere in the middle here would have been the capillary, okay? So I'm going to enter in with a specific pressure inside of the arteriole, and as I keep going down the vascular tree, all right, I will end up in the venules and my pressure will have changed. We're going to take two different scenarios to figure out how does blood flow through the actual vessels, okay? And we're going to figure out how and which of these scenarios would have the higher blood flow. Okay, so let's go through it. Now, we enter into the arteriole here with a blood pressure of 50 millimeters of mercury. And then I'm leaving the actual arteriole with a blood pressure of 10 millimeters of mercury. So if I was to take my change in pressure, my delta P would be about 40 millimeters of mercury. Okay? All right. Now let's take a look at this first. Again, we're still in scenario 1. Now let's look at another vessel. In this vessel, I'm going to enter in with a pressure of 90 millimeters of mercury, and I'm going to leave with 10 millimeters of mercury again. Okay? Again, remember, this portion is the arteriole, and this portion leaving is the venule. Okay? My delta P in this scenario would be what? It would be 80 millimeters of mercury. Okay. Now let's take the second scenario. In the second scenario, I'm entering in with, again, let's say 90 millimeters of mercury, and I'm leaving with 10 millimeters of mercury, with my delta P still being 80 millimeters of mercury. Okay? And in the second vessel, for scenario number 2, I enter in now with 180 millimeters of mercury. This is an insanely high pressure. And now I'm going to leave with 100 millimeters of mercury. My delta P here would be what? Still 80 millimeters of mercury. Okay, so in scenario 1, which of these two blood vessels do you think has the higher flow? Blood vessel A or blood vessel B? Well, it's clearly going to be blood vessel B. But why? Why? Again, this is where Poiseuille's law can help us. Poiseuille's law states that the change in pressure, okay, is directly proportional to the change in blood flow. So if my change in pressure is high, that means that my blood flow would be high, okay? And you can see that here. My change in pressure was 40, so my flow was about average. My change in pressure here is 80, and my blood flow is much higher than it was initially, okay? So why did I draw this second one? I drew the second one to prove something to you. Look, here's the exact same scenario. Okay, 90 millimeters of mercury entering in the arteriole, and then we're leaving out the venule with 10 millimeters of mercury. But then let's take a hypothetical situation. Let's say I enter in the arteriole with 180 millimeters of mercury, okay? And then hypothetical, again, I leave out with 100 millimeters of mercury. Even though I had greater pressures going in and going out, my delta P, if I were to calculate it, was still 80, okay? And so some people might think that just because I entered in with a higher pressure, the blood flow would have been faster. But really, as long as I leave out with a pressure that results in the same delta P as before, my blood flow is not changing, okay? It's staying the exact same. This is going to prove something to you. This should tell you that the pressure gradient, okay? The pressure gradient along the vessel, okay? So along the vessel determines flow, okay? Not the absolute pressure, okay? So not absolute pressure, okay? And again, remember this, that things like to go from an area of high pressure to an area of low pressure, okay? An area of low pressure. Therefore, it makes sense for the blood to follow from an area of high pressure to an area of low pressure. Okay? Awesome. And I'll expand on this idea in a second. Some of you might be a little confused as to why I'm entering the arteriole at a high pressure, but I'm leaving the venule at a lower pressure. Okay? And I'll explain this in just a moment. Bear with me. But that is the effect of a pressure gradient on blood flow. Now, we could go into resistance here, but this video will come too long. So we'll have a separate video talking about resistance and how it influences flow. And I'm sure most of you would already know that resistance is inversely proportional to flow. Okay? And one of the major contributors to resistance is going to be the radius of the vessel. Okay? Or the diameter of the vessel, which we kind of talked about last slide. Now, you know this flow, okay? You know, in vascular physiology, oftentimes you would see flow written as Q. But we saw Q as something else as well in the cardiovascular lectures. We called it cardiac output. And pressure, all pressure really is your blood pressure, okay? So we can kind of rewrite this equation, okay? We can rewrite this flow equals the change in pressure over resistance. We can rewrite it as your cardiac output, okay, which is just flow, okay? It is the milliliters per minute of flow equals to the mean arterial pressure, okay? And I'll talk about what the mean arterial pressure is, over your total peripheral resistance. Your total peripheral resistance is just a fancy word for the resistance to blood flow, okay, in the periphery. In the periphery. What do I mean by the periphery? I mean the vascular tree, okay? How much resistance is the vascular tree providing me to change my blood flow? If the vascular tree has high resistance, then I have low flow, okay? Anyways, that's that. So the concept of the mean arterial pressure, what is it? What is the mean arterial pressure? The mean arterial pressure is simply, the simplest definition is that it is the average pressure driving blood forward into the tissues throughout the cardiac cycle, okay? So it is the average pressure driving blood forward. I'm telling you right now, the mean arterial pressure, this guy right here, it is the number one homeostatically regulated mechanism in the body, okay? Like your body would let everything go wrong just to regulate this value here, this mean arterial pressure, okay? So how can you calculate it? How do you calculate it? Well, you can calculate it by rearranging this formula, okay? You could say that mean arterial pressure equals to Q times the total peripheral resistance. But you can kind of calculate it in another way too. And I'll talk about that here. So the title of this little thing is going to be called the pressure gradients in systemic circulation. Okay? Remember, pressure gradient we defined as the pressure number one when I enter the vessel and the pressure when I leave the vessel. This is kind of going to be the same thing. It's just a bigger scaled thing. So on the y-axis, I have the pressure in millimeters of mercury, ranging from 0 millimeters of mercury to 120 millimeters of mercury. On the x-axis, I have the different portions of the cardiovascular tree. I have pressure in the left ventricle, pressure in the aorta, pressure in the arterioles, pressure in the capillaries, and pressure in the venules and veins combined together. And we're going to look at this, and we're going to see how we can make sense of this. Okay, how can we make sense of this? So, first things first, the left ventricle. You can see the pressure kind of oscillates. Oscillates meaning it goes up and down, okay? So initially, I started at this 0 millimeters of mercury, and then I go all the way up to 120, okay? Why does the pressure keep going up and down here, guys? The heart is going through its cardiac cycle, okay? From one cardiac cycle to another, the pressure keeps going from 0 all the way to 120, dropping back. 0, 120, dropping back. 0, 120, dropping back. But now let's trace this pressure. As soon as it goes from 0 to 120, let's trace it and change all the way to the aorta, okay? Let's see how that pressure translates over. So we started at 0. We increase the pressure through the isovolumetric systole phase. Then we go to the ventricular systole, open up the aortic semilunar valves, boom, push the blood into the aorta at 120 millimeters of mercury. Now the pressure inside of the aorta will be 120 millimeters of mercury, and then the aorta will go through the Wind-Kessel effect, okay, and then push the actual blood away. And if it's pushing the blood away, the pressure inside of that aorta is going back down to resting pressure, the diastolic pressure. What is the diastolic pressure? It's 180, okay? So not 180, it's an 80 millimeters of mercury, okay? And the peak pressure was 120. So if you guys remember, we said that technically then we can say that the pressures on the top are going to be our systolic blood pressures, and these little pressures on the bottom, they can be our diastolic blood pressure. Another cool thing is that if I take my systolic blood pressure and I subtract it from my diastolic blood pressure, I get something called the pulse pressure. The pulse pressure, okay, which is just a difference between the systolic and the diastolic blood pressure, okay? Keep that in mind. Now, the pressure inside of this actual aorta now will keep oscillating between each cardiac cycle of the heart, where we push blood into it, and then it does the Wind-Kessel effect, bringing back down the pressure inside of the aorta to 80, and then back again, up, and then back again, down, okay? But now let's trace that pressure from the aorta down to the arterioles. So let's say it goes up again as soon as we push blood into it from the left ventricle, but then it does the Wind-Kessel effect, and it goes back down. Now we follow it into the arterioles. We enter the initial arterioles, okay? And in the initial arterioles, you can see that the pressure is kind of dying down, okay? We don't actually go up as high anymore, okay? We're at like 110 now. And this oscillating pressure is going to keep dying down as the further down this arterial tree we go, okay? So the closer and closer I get to the end of the arterioles, the lower this pressure will go, this oscillating pressure, until it just completely dies out, okay? Now, at this point, I want to introduce you to the mean arterial pressure. This black line here, okay, is the mean arterial pressure. And remember, I said the mean arterial pressure is the average pressure driving blood forward, okay? It's a pressure gradient, if you will. Now, this guy right here, okay, this guy right here is still part of the mean arterial pressure, okay? And it's about, if you can see over here, it's about 1/3 of the way diastolic and about 2/3 of the way systolic blood pressure, okay? I'm not going to go through that too much. That might be a little confusing, okay? But just know that this line resides here. It's not the perfect halfway point, okay? When I say average, a lot of people will think that it's the perfect halfway point between systole and diastolic pressure. It's not. Otherwise, it'd be 100. This value is around 93, okay? So here, we can actually write it for you. It's around 93, and there it is, okay? The mean arterial pressure is 93. But how can you calculate it? So I said you can technically calculate it if you had these values, but what if we don't have these values right now? How else can I calculate it? Well, you can calculate it like this. Let's make this prettier. So we have mean arterial pressure equals to the diastolic blood pressure plus 1/3 of the pulse pressure. Okay, what's the pulse pressure? The pulse pressure, if you guys remember, was the systolic blood pressure subtracted by the diastolic blood pressure, okay? If you go and do this formula, okay, and plug all the appropriate values in at rest, okay, you should get approximately 93 millimeters of mercury for the mean arterial pressure, okay? And that's the driving pressure at this initial point. Okay, and now obviously you can see that the mean arterial pressure is going to drop significantly. Okay, it'll drop from around 93 to, what is this number? Around 37. Okay, at the distal arterioles. Which brings me to my next point. Where does the biggest drop in pressure, in the mean arterial pressure, occur? At which level? The left ventricle, the aorta, the arterioles, the capillaries, and the venules? The arterioles. That's the answer. Why? Why is there such a big difference in pressure gradient, okay? I'll tell you why. Because the arterioles are the highest resistance vessels, and they have an extensive branching that occurs, okay? They have an extensive branching. So again, think about the vascular tree. Think about the vascular tree, guys. All right, as I'm going from these arteries into the arterioles are going to branch a lot to cover a lot of surface area of the organ, okay? And they're going to branch then finally to the terminal arterioles, which will then feed the capillaries, okay? And because they branch so much, they're going to dissipate so much pressure, okay? Imagine this, okay? Imagine this, guys. I start out with a very high pressure here, right? And I'm going, right? And this pressure is only inside of this one tube right now. But what if I keep dissipating this pressure into multiple tubes and I spread it out? Well, what do you think is going to happen to the pressure? It'll eventually just dissipate. It'll lower. It'll go away, okay? So because of these arterioles dividing so much and branching so much, that this pressure, this mean arterial pressure, will drop drastically from 93 to 37 by the time we reach the end of the arterioles. Okay, and it'll keep dropping because we keep dividing with the capillaries. By the time we hit the venules, this pressure is almost non-existent, okay? And that's why, guys, that is why the venules and the veins are low pressure systems, and they require those valves that we talked about, okay? That works out perfectly. One more thing I did kind of want to mention to you is, remember how we rearranged this formula, okay? The original one was a delta P, but we technically didn't calculate a delta P here, did we? We just went with MAP, right? Because the delta P was P1 minus P2. So there has to be a second number here, and there is. Usually it's called mean arterial pressure minus the right atrial pressure, okay, equals to the cardiac output. But why did I not mention this right atrial pressure to you? I didn't mention it to you because usually this pressure is super, super low, okay? It's around like 0 to 10 millimeters of mercury, and we don't tend to count this value as much. We just say that, oh, it doesn't make much of a difference in my calculation, so we just assume that it's negligible, and we just consider the mean arterial pressure. But if you really want it to be technical, you would do mean arterial pressure subtracted by the right atrial pressure over the resistance, which equals your cardiac output, okay? Now this right atrial pressure, it can also be called sometimes the central venous pressure, but neither here nor there. Okay. Now, let's go ahead and talk about the final topic here, which is what modifies blood pressure or the pulse pressure or the mean arterial pressure, okay? Because really, guys, if I were to increase my systolic blood pressure, okay, and if you can do the math on this over here, right? If I were to increase my systolic blood pressure, I would actually end up increasing my pulse pressure. And if I increase my pulse pressure, I'm going to increase my mean arterial pressure, okay? So right now, I'm going to look at what can modify the blood pressure. Well, many things can modify the blood pressure, okay? One of them being the compliance of the aorta, okay? Compliance of the aorta. Another one being, for example, stroke volume, okay? Another one being your heart rate, okay? And then we'll put others here because there is a specific one that I do want to talk about, okay? But the compliance of the aorta, how is it going to play a factor here? Well, if the aorta, guys, is not very compliant, okay? So let's say it's not compliant, which it usually is. If it is not very compliant, that means what? That means it's not going to be distensible. It's not going to distend. And remember, the only reason the aorta is able to distend is because of the elastin, okay? So if the aorta has a low compliance, it will not distend, and it will not perform the Windkessel effect to lower the systolic blood pressure like it usually does, which means what? Which means now this low compliance will contribute to a higher systolic blood pressure, and if the systolic blood pressure is higher, we said that the pulse pressure would increase, okay? Okay, well, in what scenarios would you see a lowered compliance of the aorta? As you age, the compliance of the aorta decreases. Here's a nice little graph here. We have pressure in millimeters of mercury over age, okay? And you can see that as your age goes from 20 to 40 to 60 to 80, your diastolic blood pressure remains pretty much the same. Your systolic blood pressure, though, sees an upwards trajectory. And because your systolic blood pressure is going up, like we said here, your pulse pressure is going to be going up, okay? So maybe initially your pulse pressure was here, but now it's larger, okay? If your pulse pressure goes up, you know what's going to happen to your mean arterial pressure? Your mean arterial pressure is also going to see an upward trajectory, as you can see, okay? So as you age, your aorta becomes less compliant, and that's got many reasons. For example, we start synthesizing more collagen, and we actually don't synthesize as much elastin molecules, and we actually break them down, and that's just because we're aging. And because of that, the aorta becomes less compliant, and that will increase the systolic blood pressure and increase the mean arterial pressure, okay? So that's one thing that can modify the blood pressure. What about the stroke volume? Well, you guys remember that heart rate and stroke volume together, right? If you were to multiply them together, what would you get? You would get cardiac output. And if you remember, we defined that we can technically say that the cardiac output equals to the mean arterial pressure over total peripheral resistance, okay? So now we can actually look at how the heart rate and stroke volume would manage to change the cardiac output, which would then affect the mean arterial pressure, okay? And I guess the better equation to use would be this one, because we could say that this guy is technically made up of the heart rate and the stroke volume multiplied by another, and if I increase this guy, I would increase this guy to increase this guy. And same thing, if I increase the stroke volume, I would increase the cardiac output again to increase the mean arterial pressure. So how does that kind of work? Well, if the stroke volume is higher, okay, that means I'm pushing more blood per cardiac cycle into the aorta, meaning I'm increasing my systolic blood pressure. And if I do that, I'm increasing my pulse pressure, which will eventually increase my mean arterial pressure. Okay? And, we'll just put a thing to map here. With the heart rate, it's all about the speed, okay? So if I increase the speed, okay, that I am pumping, that I am pushing my blood out, okay, I am also going to increase my systolic blood pressure because I'm pushing more blood out at a faster pace. And that would increase my pulse pressure as well, which would increase my my mean arterial pressure eventually. Other things include exercise. Okay, so let's say I'm exercising, okay, and here is, let's say this is an artery, okay, right here in the middle is an artery, and these are muscles that are surrounding this actual artery, okay. When the muscles are relaxed, guys, okay, their blood is just, moving forward very nicely, okay. But when the muscles start to contract, you know what they do? They actually squeeze and block and occlude the actual, the artery, okay, meaning that the blood that was initially here will now be pushed outwards, okay? It'll be pushed outwards to all the other open vessels. The blood that is being pushed out to the open vessels will cause a transient, but very, transient just means short. The blood that's being pushed from this vessel that's being squeezed into adjacent vessels that are currently open will increase the blood pressure inside of those vessels very sharply, but transiently. Okay? Why? Well, because they already had a resting amount of blood in them, but now I squeezed these and forced that blood into any open vessel nearby, which increased the blood volume inside of that vessel, pushing on its walls and increasing its pressure. Okay? What would that look like if I were to graph it? Okay? So let's say I'm doing some sort of repetition exercise, okay? And with each rep, my blood pressure is going to go up and down and up and down and up and down. So here it is. This is the start of the exercise. I do my first rep here, okay? I contract, blood pressure goes up, I relax the muscle, okay? So look at it, I contract, this is what's gonna happen, okay? I'm gonna push the blood into the open vessels and increase their blood pressure, and then I'm gonna relax, and then stop occluding that blood vessel and allow blood to flow again, which will decrease the blood pressure, okay? And then I contract again, it goes up, and same thing, okay? I can keep doing this. And I would reach, values maybe sometimes as high as 300 millimeters of mercury for my mean arterial pressure, okay? So that's one way that exercise can modulate the activity. But let's say I'm doing a very sustained exercise, and I keep increasing the intensity of that exercise, okay? If I increase my exercise intensity, okay, and this is for exercise that's very much sustained, exercise intensity increases, whether it's upping the weight or increasing the duration of my running, okay, the speed of my running, I'm going to activate my sympathetic nervous system, okay? I'm not going to go through the pathway here. I've already covered this in my exercise physiology video. If you're interested, go and watch that. But this increasing in exercise intensity will be sensed by specific mechano and metaboreceptors at the level of the muscle, which will feed back to the brain and increase sympathetic nervous system activity, plus lowering parasympathetic nervous system activity in the same time. This will have twofold effects, okay? The decreased parasympathetic nervous activity will have an effect on the heart rate, but don't worry about that. Right now, we can say that the increased sympathetic nervous system activity would increase our stroke volume, and we know this from the regulation of cardiac output video that I put out. Another thing is that the increased sympathetic nervous system activity will increase vasoconstriction. And if you guys remember, I mentioned that arterioles, for example, are highly innervated by a sympathetic nervous system, and if they innervate those smooth muscle cells, they will cause vasoconstriction, which is just the smooth muscle cells contracting and decreasing the lumen of the actual, or diameter of the vessel, the arteriole specifically. If I have a high vasoconstriction, okay, meaning that my vessel diameter, instead of being this big, is now this big. Okay? What do you think is going to happen to my blood pressure? Okay, is blood going to exert more force on the walls in this scenario where it has more space, or in this scenario where it has less space? Probably this one, okay? Because now, remember, it's just Boyle's law, okay? Pressure and volume, okay? If I increase if I decrease the volume in a given area, I will actually end up increasing the pressure in that given area, okay? And that's exactly how it works. So if I vasoconstrict, I'm decreasing the volume inside of the actual vessel, and I'm increasing the pressure inside of it, okay? So, and same thing with the stroke volume that we said over here, okay? If I increase my stroke volume, I'm increasing my systolic blood pressure. All this to say that I'm going to increase my systolic blood pressure, okay? And of course, the vasoconstriction can also contribute towards resistance, total peripheral resistance. But really, in this slide, we were talking about what modifies blood pressure. So now we know exercise can modify it in two ways, via the sympathetic activity and this little mechanical action that I was just talking about, okay? All right, guys, that's going to finish it with the introduction to the vasculature and a little bit about mean arterial pressure. If you truly enjoy the video, please consider liking, consider subscribing, and I will see you in the next one.